In this video, I'm going to continue showing you how to graph rational functions and hopefully try and explain all the little different subtleties that will happen. In this video, we're going to focus on holes, which are little holes in our graph. They're open circles, undefined points. And then if we got some time, we'll get into slant asymptotes. So let's start with what are holes, what do they look like, how do they happen? So here's a rational function. In general, anytime you want to graph rational functions or deal with rational functions, it's always best to simplify first. So see if you can put it into a factored form, because we'll get a lot of information out of that form as well. So we'll need this form, and then we'll also need a more simplified form or a factored form. So if I factor the top here, if I take out a 4 from both terms, just taking out their greatest common factor, and I'm left with x minus 4. And if I use a little quadratic pattern, factoring pattern on the bottom, I can factor that quadratic. 2 sets of parentheses, an x to start with in each one. And then I need factors, or numbers that multiply, to give me 8, and then add up or combine to make -6, that middle term there. So I know that 4 and 2 are factors of 8, and if I actually make them both negative, then they would combine to give me a -6 and multiply to give me a +8. So there's our factored form. We're going to get some information out of this. Right off the bat, you can see that x minus 4 happens at both the top and the bottom of our ratio here. And in a lot of ways, you've been taught to cancel things that are like terms on top and bottom of ratios. And that's also true with rational functions. This and this simplify and go away. And really, our function will end up being 4 over x minus 2. That'll be the rational function that we actually end up graphing. So right here is where your hole happens. What value for x would make this whole thing go away? Well, if I plug in a +4, that would make this whole thing become 0. That would make the bottom all become 0, and then I would have an undefined output, or an undefined function at that value. So x cannot equal +4. Or, there's another way that we can say it. We can say a hole exists at the value of x equals 4. So either way you want to say it. X can't equal 4 because it's a hole, or you can say that the hole exists where x equals 4. So when we'll put a little, I don't know, we'll put a little star there just to remind ourselves that we're going to do something with that in a second. So that's where holes happen. If you can factor the top and bottom, the numerator and denominator of your ratio here, and you are able to cross off any like terms, if it's an input that we're crossing off, state that input value and either say that it can't be that value because it's undefined, or that the hole exists at that value. And we'll draw it in a second here. Let's figure out how else we can graph this. If you know how to graph rational functions, or if you watched my previous video, we talked about 4 steps to help us graph. And the first step was to find and plot our x-intercepts. So let's do that right now. X-intercepts happen where y equals 0, and that's also an output. So if my output equals 0, how can I find a value where my output equals 0? Well, if I make the top of my fraction equal 0, then the whole thing will equal 0, because 0 divided by anything is 0. So if I just find zeros on my numerator, that'll give me my x-intercepts. So if we look right here, really there is no zeros. I mean, it used to be 4, but if we plug in 4, we end up getting a hole, so that's no longer our intercept. So we're going to leave it blank still, and I guess we don't have an x-intercept. That's okay, sometimes that happens. So next we'll look for y-intercepts. Y-intercepts are where x values are 0. So anywhere on the x-axis, we're looking for y-intercepts. that's right here, so the x value would be 0, right? So if I plug in 0 for my x, then my output should be the coordinate pair of my y-intercept. So I'm looking here now because it's a lot easier to use. And if I plug in 0 for x, what do I get out of it? Well, I know I have 4 on top. And if I plug in 0 here, I get 0 minus 2, which is negative 2. So I have negative 2 on the bottom, and that equals negative 2. 4 divided by negative 2. So if I plug in 0, I get an output of negative 2. That's my coordinate pair, or my y-intercept right there. Okay, we'll label it. Alright, so let me get rid of that, give myself some more room. So we found our intercepts, and now we look for the asymptotes. We're going to start with the vertical asymptote, and the vertical asymptote trick is just to look for zeros at the bottom. Well, we know it's not 4 anymore, so there's really only one option for a 0 of the denominator here. If we plug in 2, we should get a 0 on the bottom. So my vertical asymptote would be a vertical line, which is an x equals equation. And if I say x equals 2, that's an undefined place on my graph. So there's my vertical asymptote. Draw a dashed line at the value of x equals 2, that vertical line. And there's our vertical asymptote. Alright, so we're done with those. Let's look for a horizontal asymptote if it exists. There's always 3 checks you need to do. Make sure you know all 3 of them. You can look on our last video there to learn those tricks. But anytime we're looking for a horizontal asymptote, we're comparing the leading coefficients and their degrees, or their exponents there. So we have a 4, and we got an x on the bottom. Well, that x degree right there on the bottom is greater than my degree on the top. And if that's true, then we know that our horizontal asymptote is always, it's always y equals 0. Or in other words, it's always the x-axis. So if the top degree is less than the bottom, this is always true. Or if you want to state it a different way, it still means the same thing. If the bottom degree is bigger than the top, then you got this horizontal asymptote. So it's a y equals equation for a horizontal line. Y equals 0 is the x-axis. So we'll just keep that in mind, that the x-axis is our horizontal asymptote. You can make it dashed if you want, but it's just going to get in the way right now. So let's get rid of that, give ourselves some more room here. There's one more asymptote that you usually want to look for, but that's only if there is no horizontal asymptote. So that's only if the top degree is bigger than the bottom. We may have a slant asymptote, and I'll try and take you through that in the next video. I don't think we'll have time in this one. So we should have everything we need. We got our intercepts, we know where a hole may exist here, and we got our asymptotes all graphed out and plotted and drawn. So now the last step is to just plug this into your calculator if you got one, and look at the graph and make sure it matches with all the information that we've already plotted. Now we can go the slow way. We can input values, come up with an XY table, and really plot individual values there, but if we got the technology, let's go ahead and use it, save ourselves some time. So really, we're using the calculator as a way to check, to draw our lines, which is the last step anyways. And we've pretty much done all the work anyways, just drawing our asymptotes and our intercepts. But again, you can come up with an XY table if you really want to go about it the long, hard way. Alright, so when I plug this into my calculator, my graph tells me that it looks something like this. So right there, got a slightly curved hyperbola here crossing through my y-intercept and approaching my vertical asymptote but never touching. And in this case, it happens to not cross my horizontal asymptote, although it may sometimes. On the other side here of our asymptote, we got another hyperbola. And this one is going to look something like this. We'll stop right there, I'll continue it on down here. So again, coming close to our x-axis, which is our horizontal asymptote. In this case, it's not crossing it, but sometimes it might. Over on this side, it's approaching that vertical asymptote, but never touching, never crossing. And then right here, where we said we had a hole at x equals 4, sometimes you won't see it especially on your graphing calculator there. But if you look at your table, if you can find that table on your graphing calculator and you look at x equals 4, it will say undefined, and that means that we have an open circle. It's not defined right there at that spot on our graph. You can draw it with an open circle, or sometimes if you just state that x can't equal 4 because it's undefined, you could go ahead and just draw it straight through there. So there's an example of a rational function with a hole in it. Again, if you are able to factor and cancel any like terms on top and bottom, that is a good idea of where that hole might be. And you can state it two different ways. You can say that the value cannot equal that value, or x cannot equal that value because it's undefined, or you can say your hole exists at that value. They mean the same thing. Alright, so good luck graphing rational functions that have holes in them.